Hello, this is Lisa Knight, and this is the second of 2 lectures on electric circuits. In this lecture, we will talk about resistors in series and parallel and Kirchoff's rules. Resistors connected end to end are said to be in series. The definition also implies that there's one current loop. So if you look at figure A, you start at the battery and you start tracing from positive to negative. Even though there are 3 different resistors, there is only one path of current, I. Together, these resistors act like one big fat equivalent resistance. To find that equivalent resistance, all you have to do is add all 3 resistors. So the equivalent resistance of resistors in series is R1 plus R2 plus R3 and so forth. If I have a 20 ohm, a 30 ohm, and a 10 ohm resistor connected in series to a 120 volt source, what is the equivalent resistance? The equivalent resistance would just be 20 plus 30 plus 10 or 60 ohms. Furthermore, if I want to find the current in each resistor, I can use Ohm's law for each resistor. If I rearrange V equals IR for I get I equals V over R. So the current in the circuit would be equal to the current in the total resistance. The total resistance determines how much current each resistor has. So I take 120 volts and divide it by 60 ohms. And that means there's 2 amps of current in the circuit total. So if we go back and we look at our picture here, each resistor has the same amount of current flowing through it. But that means that if I apply Ohm's law to each resistor, they do not share the same resistance as the battery. For example, if R1 is 20 ohms and the current is 2 amps, V equals I times R, or 2 amps times 20 ohms, and that is equal to 40 volts. So there's a 40 volt drop in potential across this resistor. And then I could find the voltage drop across this and the voltage drop across this using that same formula. If you notice, there's 40 volts of drop across the 20 ohm resistor. 2 times 30 gives you 60 volt drop across the 30 ohm, and 2 times 10 gives you 20 volts of drop in voltage across the 10 ohm. So if you add all those together, they add up to be the voltage of the battery. So if you visualize this one more time, the voltage here plus the voltage here plus the voltage here equals that of the battery. So V1 plus V2 plus V3 equals the battery's voltage, or the total voltage, or the EMF of the circuit. But they all have the exact same current, which is found using the equivalent circuit here. When resistors are in parallel, it's different. If you look at this particular example, circuits that are in parallel have more than one current path. So I start at the battery and I have the total current, but when I get to the first junction, some of the current goes into R1, some of it goes into R2, and some of it goes into R3. So in a parallel circuit, the currents will be different if the resistances are different, and they will not necessarily be the same. When they all join back together, they add up to be the total current of the circuit. Once again, the resistors are acting like a resistance, but together, because there's 3 different paths here, there's actually more current able to flow in the circuit, and so the total resistance is less than any of the single resistors. The total resistance of a parallel circuit is 1 over R plus 1 over 2 plus 1 over 3. That means that if I want to find the total resistance, I have to go one more step and take the inverse of this to turn it over so that it says R equals something. Here's an example. If I take those same resistors, 20 ohm, 30 ohm, and 10 ohm, and I put them in parallel, then the total resistance, 1 over Req, equals 1 over 20 plus 1 over 30 plus 1 over 10. If I put that in my calculator, or if I find a common denominator here, I'm going to get some kind of decimal or fraction. I need to take the inverse of that, and I'll get a total of 5.45 ohms. So together, these are acting like one little resistor of 5.45 ohms. The voltage across each one is the battery, because let's go back to that picture again. If I block out R2 and R3, the battery is connected directly to R1. If I block out R1 and R3, the battery is connected directly to R2. So the voltage drop across R2 would also be that of the battery. And if I block out R1 and R2, then R3 is connected directly to the battery. So the drop there would be equal to that of the battery. So unlike a series circuit that has the same current in every resistor and different voltages, a parallel circuit is going to have the same voltage across each resistor, but different currents. So now if I plug in to Ohm's law, and I use V equals I over R, I get I1 is equal to 120 over 20 ohms, which is 6 amps. I2 is equal to 120 over 30 ohms, which is 4 amps. And I3 is 120 over 10 ohms, which is 12 amps. If I add up all these amps, right, I get 22 amps, which is equal to the total current of in the circuit. Note, you could also find it by taking 120 divided by the total resistance, which is 22 amps. So we have some fundamental differences. What if you have a circuit that has a combination? The strategy is to identify which resistors are in parallel and which ones are in series. So if you think about this, start at the battery and start here and you go, and so the total current goes into R. But when it gets to this first junction, some of it goes into this R and some of it goes into this R. So these two are in parallel with each other. So they're acting like one resistor. So I'm going to call that one resistor here. One total resistor, a little teeny resistor. And it's acting like it's in series with these. So this resistor and this resistor and this resistor are going to have the same current going through them, which I can find using their total resistance and the total battery voltage. They are going to have individual amounts of current going through them, which means they have different voltages going through them. The voltage here across R over 2 is equal to the voltage for this resistance and the voltage for this resistance, because this resistor is really these two resistors in parallel, and resistors in parallel have the same voltage drop from here to here, which is identical to here to here. So in more complex circuits that have like more than one battery, you have to break this down to something called Kirchoff's rules. The junction rule says that as you go around a circuit at a junction point, the current going into a junction point is equal to the sum of the currents coming out of the junction point. So in this case, I1 is equal to I2 and I3. In the loop rule, the potential difference around a closed loop must be 0. So let's just define what a gain in voltage is and what a loss in voltage is. When the current goes through a gain, When you gain energy, you're going from a negative to a positive polarity. So if you're going up through this battery, you're gaining voltage. But because the resistor is connected to the positive terminal here and the negative terminal here, when the current goes this way through the resistor, comes through, comes around, it's always attracted to the negative side of the battery, it's coming back down, it's actually going from a positive to a negative, like it's going downhill, and it's going to have a voltage drop. Now, what does that mean? It means that, think about it, by the very nature of a resistance, if the current is trying to go from positive to negative, it doesn't really want to do that, right? Because really what we have here, we really have electrons that are moving, right? The electrons don't want to do that, so there's a natural amount of resistance here, so we're going to gain some heat. Some of our potential energy is going to turn into heat here, so we have a voltage drop. The total sum of all the gains is equal to the sum of all the drops. So the gain in voltage is from your battery power, and your gain in drops is going across resistors. The variables for which you're solving are the currents and the resistors. You may need as many independent equations. So when you do these Kirchoff problems, you have lots and lots of, you have more than one equation. So I have provided some sample problems in this module that go through and give you some examples where you have to use Kirchoff's rules. And I suggest that you look at those and watch those.